Hey, Cat BC, Unit 4, Day 4 lesson. We're going to talk about polar derivatives a little more. So, just a quick refresher. We do a quick sketch of a common polar curve, just as an example, like y equals 1 plus cosine theta, which is a cardioid. We make a quick table. We expect it to be horizontal because of the cosine involved. So it's going to be 2, 1, 0, 1, 2. So actually, hold on a second. Maybe I'm doing the wrong. Let's see. Let's put a minus right here. I'm going to change it up a little bit just to fit my graph better. So then that would be 0, 1, 2, 1, 0. So I'm just going to change it. So it's a little easier to fit on this graph. So 0, 0 is right here. Pi over 2, 1 is right here. Pi 2 is right here. And 3 pi over 2, 1 is down here. And then you're back to there. So it looks, this is very round. Okay. So something like that. So we're talking about dy dx in the last lesson, and dy dx is simply the slope along the curve, just like it always has been. And drd theta is how the radius is changing with respect to theta as theta changes. So, you can just look at the slopes, and I'll come back to that in a second. But, this whole time right here, drd theta is positive. The radius is getting bigger as we go, as the angles get bigger. And here, for this whole chunk, drd theta is getting smaller. And at this point right here, drd theta equals 0 because it's going from positive to negative, so it's got to go through 0. And here it might be like undefined because that's like a cusp, right? And so it jumps from, maybe it's 0. I guess we could see in calculations. Now, dy dx, the way we find the slope of the curve is just by doing dy d theta over dx d theta. Now, originally in my notes, I'd written out one of those formulas I wrote the other day, but I'm never going to write those again because this is a waste of time. X equals r cosine theta, y equals r sine theta. You should be pretty good at those. So the one thing you got to be careful about is that the y's are on top and the x's are on the bottom. And sometimes you might instinctively start with x like I do often when I'm writing these equations, and accidentally put them on the top or something, put it upside down. Now, let's get a little more into some specific cases, like what if we want to know when it has a horizontal tangent? And sometimes these polar problems get mixed in with parametric, so you might be thinking motion, like flying horizontally or something. Now, a horizontal tangent, if you look at your picture, there are at least those two, and then maybe like one right here because it's coming in at, it looks like it's flattening out. So there might be 3 in this picture, but it's going to be specifically when the slope is 0. That's what we've always done to find horizontal tangents. And that's going to be more specifically that the numerator of our expression for dy dx is 0, and that dx d theta is not 0 at the same time, but it could be. Okay, if this is true, then it's for sure horizontal. If they're both 0, then we're going to have to maybe use L'Hopital's rule. It might turn out to be one or the other or neither. A vertical tangent would be when it's straight up and down. So there, here, here. So with sketches, you can see how many you expect to get, where they're at, and so when you go to find them, um, you'll feel more confident. Now this is going to be when the slope is infinitely steep, so it's undefined because it's being divided by 0. So because it's being divided by 0, that means the denominator must be 0. And hopefully dy d theta is not 0 at the same time, even though it could be. It just complicates things. And I'll probably try and show you an example in the back of where that happens and how we could deal with it. We're going to use L'Hopital's rule for sure. So this is just, kind of a little review of yesterday, and maybe add in a couple things. So let's find the equation of the tangent line. So that's a very common question over the year and a half of calculus that you've been in, and really you need a point and a slope. We could draw a sketch of the graph to kind of get a rough idea of where that should be located and what the slope should look like. So I'm going to do just a quick sketch of the graph. And by the way, that's just good practice. So if you want, you could pause this and see if you could sketch it yourself, see if you're getting the hang of it. So if you want, pause it, and then I'm going to continue. Now, when I sketch this is a rose curve, okay? And I can tell because of the extra number on the inside. It's odd, so that means there will be that exactly number of petals, and it'll take 0 to pi to graph it. This is the radius of the rose curve. So I would start by sketching a circle that it will fit perfectly inside of, with a radius of 2. And this is going to be a light circle, and all these little dots are light because they might not even end up on the curve. All right, so there you go. And then I'm going to try and figure out where the tips of the petals are. Just kind of the center of the petals, and you're going to set the radius equal to the extreme radius of the circle, which is going to be on the edge of that extreme radius of the rose curve, which is going to be on the edge of that circle. I mean, right away the 2's go away, so I guess if you want to, you could just jump to that and ignore the 2 and set it equal plus or minus 1. Sine equals 1 at pi over 2 plus pi k, positive 1 and negative 1. So theta equals pi over 6 plus pi over 3k. And so we're going to be looking at, like I said, we just need the first 3 petals. So pi over 6 and pi over 2, because it's going to be 2 pi over 6 plus 1 pi over 6 is 3 pi over 6 plus another 2 pi over 6 would be 5 pi over 6. So that should do it. And so I'm going to sketch those angles in. Now I'm going to start with pi over 3 because I feel like that's easier to get, and 2 pi over 3 all the way through. And then pi over 6 would split those in half. And you need those angles anyways because those are going to be the edges of your petals to make your picture look good. So the first one's at pi over 6, and it's going to be positive because that's when sine hits a max right there. So this is going to be the first petal. And then pi over 2 up here, it's going to end up down here. That's going to be the second petal. It's going to have a negative radius. And then 5 pi over 6 is over here. I go ahead and label these. And it's going to be positive. And it should kind of look like, okay, it's going to be a kind of a distributed group of 3 petals. So it's going to go like this. It's going to start here and go like this. And it's going to come in like a tangent, right? And smoothly go into the next one. And then come into that at a tangent. And then come through smoothly into the next one. And then it should continue on. So it's a pretty good sketch for rose curve. Now, we're specifically interested in pi over 6. So right here, that's pi over 6. And this is the tangent line that we're trying to find the equation of a line for, right? It should have a negative slope for sure. Okay. We need the xy pair of points that are at that point right there. Now, the way we're going to find them, and we could have done this without a sketch, but the sketch just kind of helps show you what's going on. You can use x equals r cosine theta, which is going to be 2 sine 3 theta cosine theta, and y equals r sine theta. We use these all the time. And then plug in the expression for r, that's in terms of theta. So we have expressions for x and y, and we can actually use those to find the x and y coordinates for our tangent line. So we're going to plug pi over 6 in. And we're going to get pi over 2 and sine of pi over 6. And so that's going to be sine of pi over 2 is 1. Sine of pi over 6 is 1/2. So that's just going to be 1. That's your x coordinate. Actually, hold on a second. I messed up. Oh, I messed up because this is cosine. Cosine. I wrote sine. So this should be root 3 over 2. So this is going to be root 3. And then y is going to, I think, be the value we just got. I'm going to plug pi over 6 in here. It's going to be pi over 2. And then sine of pi over 6 is what I accidentally did on the last one. It's going to be 2 times 1 times 1/2 is 1. And that's the y value. So you have your point that you're going to write your equation, your tangent line through. So that's part of it. And then the other part is we need the slope. So that's going to be dy dx. And we know that dy dx is going to be dy d theta over dx d theta. And we don't need any formulas for that because let's just take the derivative of what we have up here. Use product rule, 2 sine, 3 theta, derivative of cosine is negative sine. Oh, I'm making a mistake. I think I was mentioning you got to make sure I was doing dx on the top, but it's dy. So that should be cosine and then plus sine theta times 6 cosine 3 theta. Don't forget the chain rule. All over. Now we do the derivative of x, 2 sine 3 theta, negative sine theta plus cosine theta times 6 cosine 3 theta. Okay, and then we're going to plug theta equals pi over 6 into here. So, you know, I don't know, I might try and do a bit of that in my head. So that's going to be sine of pi over 2, which is 1, cosine of pi over 6, which is root 3 over 2, plus sine of pi over 6 is 1/2, and cosine of pi over 2 is 0. And then sine of pi over 6 is 1 times negative 1/2 plus cosine of pi over 6 is root 3 over 2 times 6 times cosine of pi over 2 is 0. So these terms drop out and we end up with root 3 over negative 1, or just negative root 3 for the slope. So the equation of the line now is super easy. It's y minus 1 equals negative root 3 times x minus root 3. Point slope forms, good enough. Now something I want to point out that happens is, you notice how these, whenever you have terms, some of these terms dropping out, like that might be some kind of special case. And this is a special case because we're out at the very extreme point on the rose curve. And by the way, another way of finding those locations would be, that's where dr theta, or r prime sometimes, equals 0, because the radius is getting bigger, bigger, bigger. Now it's getting smaller, smaller, smaller. So, and that kind of makes sense because that's a maximum radius. So it's kind of extreme value theorem idea that you would find the critical points of the thing you're trying to maximize are, take its derivative, set it equals 0, and you get those locations. And by the way, that's what that's what these terms right here are that had the zeros. The 6 cosine 3 theta came from the derivative of this, which was the r value. So if you know you're there, you could, I guess, potentially just ignore those. But we'll talk about some kind of shortcuts to help with that stuff. But Anyways, there you go. Kind of just an old kind of problem connected to our new ones. Find the equation of the tangent line. And let's see. Find the slopes of the tangent lines at the pole. So that would be if it goes through 0, 0, which I expect it to. Let's do a quick graph of this. Now, this is not a cardioid. This is probably a limacon of some type. Does it have inner loop? Is it convex? I don't even need to remember that because if we did a quick table, it'll I think become obvious if there's that extra dot in the inside of it or the outside of it. So 0, pi over 2, pi, 3 pi over 2, 2 pi. You guys should be getting good at this. Sine 0 is 0, so it's 1. Sine pi over 2 is 1, so it's going to be negative 1. 1, 3, and 1. Should be vertical because it involves sine. And biggest radius is downwards at 3 pi over 2. So like if I'm trying to sketch this and use the least amount of paper to get a good sized graph, I'd go with that. So 0, 1's right here. Pi over 2, negative 1's right here. So right now I think it's an inner loop. Pi 1's there, 3 pi over 2's here, 3, and it's back here. So you can tell right there, that's an inner loop. So it's going to go through these poles right here. So if you're to sketch this, it's going to go like that, like that. So something like that. Limacon with an inner loop. That's what, I knew it was going to be a limacon. I mean, the whole family of curves is called limacons. Cardioids are technically limacons, but they ended up with having an inner loop. So we're really interested in the pole here, and we want to find the equations of the tangent lines. And I would say there's 2 of them. It goes through the pole twice, and it almost looks like they might be perpendicular to each other. Maybe that seems possible. We got to figure out, well, when does it go through the pole? We need the angles because we need those to do all the stuff we just did on the last problem. And we already have the x and y coordinates. It's at 0, 0, so that makes it easier. But to find when it goes through the pole, set the radius equal to 0, because that's when that happens, and solve the resulting trig equation. Quadrants 1 and 2. So theta equals pi over 6 and 5 pi over 6. That should make sense if we were to put those in here. Pi over 6 would be right there, and that goes between when it goes from 1 to negative 1. It goes from this point to this point, right? And it has to go through the pole in between those. So it makes sense that we go in there. And then 5 pi over 6 would be right here. So between this point and the next point, it goes through the pole again. So that makes sense that those are the angles. It's hard to think of them as in like quadrants and stuff, but okay. So we need x equals r cosine theta. I always just write that down, and then I write that in there. And I don't need any other formulas other than these really basic x equals r cosine theta and y equals r sine theta, which we use all the time anyways. So I just write those down. Okay, we don't need to find x and y. We already know it's 0, 0. I mean, if you want, you can go ahead and plug these 2 numbers into both of these, and it's going to come out to 0, 0 for both of them. And this is a special case. So then we're going to do dy dx, sorry, which is dy d theta over dx d theta. And so dy d theta is going to be 1 minus 2 sine theta. Derivative sine is cosine plus sine theta. That's going to be negative 2 cosine theta. Product rule. The bottom is going to be 1 minus 2 sine theta. Cosine is negative sine. And then cosine times derivative of that, it's going to be negative 2 cosine theta. Now, we could go ahead and now calculate these at both of these points, but I want to point out a shortcut. So, I mean, we can do all that, but here's the deal. When you're at the pole, special case, what do you know? You know that r equals 0. Well, this right here is r, right? This is r. This is r right here. This is r right here. This is for sure going to end up being 0. You can do the calculations, it's going to be 0. So these whole terms drop out. And then you're left with this, okay? And I mean, even before we do any calculations, we could say, okay, well, in this special case, dy dx ends up just being this term on the top and this term on the bottom. And look what else happens. Well, both of these were the derivative of the radius, which has a value. Okay, but they both have a cosine. So the cosines cancel, the negatives cancel, the 2's cancel. And what do we get for dy dx in this very special case? Tangent theta. This is a shortcut. Okay, you don't have to learn it, but it definitely it's definitely a lot simpler. So now at theta equals pi over 6, dy dx, we could just plug it into that. And in this case, I'm going to do sine pi over 6 over cosine pi over 6, because I don't really want to memorize tangent values. So that's going to be 1/2. That's going to be root 3 over 2. That's going to be 1 over root 3. That's going to be root 3 over 3. That's the slope. And we're just trying to find the slopes of the tangent lines, not the equations. And so then at theta equals 5 pi over 6, dy dx is going to equal sine of 5 pi over 6 is going to be 1/2. Cosine is going to be negative root 3 over 2. Same reference angles, quadrant 2 though. And they're not perpendicular to each other, but they have the same values and they're just the negative of each other. Anyways, this is kind of a cool shortcut because what it does is it lets us not calculate all this stuff, which we usually will. So this is just in, case when you're at the pole, which comes up enough that I think could be worth remembering this shortcut. Okay. But you don't have to use it. You get these same answers. But in this very special case, this is only at the pole that you can use this shortcut for dy dx, just at the pole. Now, here's another problem. We can do a quick sketch. This is a cardioid because the coefficients are the same. So we can do a quick sketch. 0 pi over 2. I just think this is going to help you catch some mistakes potentially. And shouldn't take that long. You should be pretty good at just quick sketch. So that's going to be 2, 1, 0, 1, 2. It's going to be horizontal. It's going to be bigger on the right side. So So 0, 2 is here, pi over 2, 1's here, pi 0 is here, 2 pi over 2, 1's here. And it looks like that. So quick sketch, right? So we're going to answer a bunch of questions about this. So I think this sketch we want to maximize R. Where's R the biggest? Now in my picture, I'm thinking that that's right there. I feel like this is probably your max R. Now we're going to show work to find it because usually we're not going to picture, and some of these polar shapes could get weird, but I think this helps us right now. I believe it's going to be there. Now to find the maximum R, this is like, extreme value theorem. You want to find the critical points. We're going to take the derivative of R with respect to theta, or R prime, and that's negative sine theta, and we're going to set it equal to 0 undefined to find the critical points. So theta equals So sine theta equals 0. So theta equals 0 plus pi k. So theta equals 0, pi, 2 pi. Those are your critical points. And we could even do a table with endpoints. So the endpoints are some of these critical points. Plug these into R, which is 1 plus cosine theta. So I think we already found these values, right? 0 is at 2, pi is at 0, 2 pi is back at 2. So there's the min. These are the maxes. So there's one max radius, but it happens at 0 and 2 pi. So I guess we could list it both. It's really the same point, but there are multiple angles that it happens at. Okay. So sure enough, the max radius was 2, and this is where it happened. So picture kind of helped confirm that. Let's see. Let's find the slope of the curve when R is maximized. Now, from my picture, I expect that to be undefined. Okay. X equals R cosine theta, which would be 1 plus cosine theta, and Y equals R sine theta. I'm going to show you guys a shortcut on this one too. 1 plus cosine theta, sine theta. So then we would do dy dx. We're trying to find the slope, which would be dy d theta over dx d theta. So dy d theta would be 1 plus cosine theta. Temperature of sine is cosine, plus sine. Temperature of 1 plus cosine is negative sine, all over 1 plus cosine theta. Temperature of cosine is negative sine, plus cosine. Temperature of 1 plus cosine is negative sine. Now, what I want to point out before we do any calculations, now we can do the calculations right now and say, okay, well, let's find dy dx at theta equals 0 or 2 pi. It's going to be the same, right? 0 and 2 pi is going to give you all the same answers for these. So either one of these, we can just do one calculation. So cosine 0 is 1, so we're going to get 2 times 1 plus 0 times 0 over 2 times 0 plus 1 times 0. We get 2 over 0, which is undefined, just like we thought it would be from the picture. So that's the slope of the tangent line where, the slope of the curve where R is maximized. Now, you see all these different terms dropping out? That might be a special case. And sure enough, when R is maximized, when you're looking for max R, right? When you're looking for max R, you know that drd theta is going to equal 0 because it's going to happen at these critical points, right? And in your calculations here, these are drd theta. This is your drd theta. This is your drd theta, right? So you know those terms are going to be 0 in this special case. So these terms just totally drop out. And then you're left with this, but the 1 plus cosine thetas, which is the R, is the same on top and bottom. So they go away. And so you get dy dx equals negative cotangent. That's a shortcut for finding dy dx at max or min R. So you could use that one too. You don't have to, but just kind of, the work wasn't that bad to do without the shortcut, but I don't know. Some cases, maybe that might be nice. Okay. Now, what if we're looking for vertical tangents, horizontal tangents? So vertical tangents are going to be when the slope is undefined, right? It's going to be infinitely steep. Specifically, that's going to happen when dx d theta equals 0. So dx d theta, using our expression for x over here is going to be 1 plus cosine theta times negative sine theta plus cosine theta times negative sine theta. And so we just need to solve this equation. So we're setting it all equal to 0. I think we could take a negative sine theta out of both of those, and then there would be a 1 plus 2 cosine theta left equals 0. So I'm doing a little factoring here. So it's going to be when sine theta equals 0 and when cosine theta equals negative 1/2, sine equals 0 and theta equals 0 plus pi k. And this is going to be reference angle pi over 3, quadrants 2 and 3. And now look at our picture. We expect to get vertical tangent here, here, and here. I think there's 3 of them. So now this is going to give us 0, pi, 2 pi, and 0 and 2 pi are the same. And this is going to give you 2 pi over 3 and 4 pi over 3. Now, I just told you I expect to get 3 answers, but this is giving us 1, 2, 3, 4. So that probably means maybe we missed one or one of these is not the right answer. So I'm going to come back to that in a second and show you what's happening. But for now, we'll put them all on here. But there might be something wrong about this answer. Okay, those are the locations of vertical tangent. Those are the angles. Let's find the horizontal tangents. Now on our picture, expect one here, here, and I would say at the cusp here. When the cusp is sideways, that's going to be a horizontal tangent. If the graph is up and down, I think that would be a vertical tangent. So I think we're going to get 3 answers. And so we need to, horizontal tangents are going to be when you get a flat slope. So that's going to be when dy d theta, the numerator of dy dx, equals 0. And so dy d theta is going to be 1 plus cosine theta times cosine theta plus sine theta times negative sine theta. Do a little quick product rule there. And then we could factor this. We could take I don't know if we can factor it. Let's see. I think we get cosine theta plus cosine squared theta minus sine squared theta equals 0. So how are we going to solve this? Well, quick trick, Pythagorean trig identities. We could replace this with 1 minus cosine squared theta, right? Is everyone following that? Because sine squared plus cosine squared always equals 1, right? That's the Pythagorean trig identity. So if I solve for sine, I get 1 minus cosine squared. So then that way I get an equation that it's like it has all the same variables, so I could actually factor it. So you're subtracting a negative here. So it's going to be 2 cosine squared theta plus cosine theta minus 1 equals 0. So then I'm going to factor it. 2 cosine theta. It's going to be a 1 and a 1. One's got to be positive, one's got to be negative, but you want a positive 1 cosine theta when you're done. So this one's positive, that one's negative. So then cosine theta equals 1/2, and cosine theta equals negative 1. So this is reference angle of pi over 3, quadrants 1 and 4. So theta equals pi over 3 and 5 pi over 3. And here, theta equals pi, right? Theta equals pi plus 2 pi k. So these are our answers here. Now we expected to get 3 answers, and we got 3 answers. But check this out. Let's compare these to the answers we just got on the last problem over here. Do you see any of them repeated? Pi gets repeated. It can't be horizontal and vertical at the same time. It can't. And if you look at the picture, I would say clearly at pi, it is horizontal. So the picture can help you avoid that mistake. And I'd be all for that on my next test. But how would we figure that out without a picture? One, you'd have to realize that if it shows up in both of them, then that's a potential bad problem. That doesn't mean it's not one or the other. It might mean it's neither. It can be both. And this is what I was talking about in the front when I said, hey, when you want to find horizontal tangents, you want dy d theta to be 0, but not dx d theta at the same time, in the same way for the other one. If that's true, it doesn't mean it's not horizontal or vertical. It just means it's more complicated, like in this case right here. Now, algebraically, the way we would figure it out is we'd say, okay, well, what would happen is that dy dx, which is what we're specifically looking for, okay, dy dx, which we wrote expression for over here. I'm going to go ahead and clean this up. I'm going to say that this is cosine theta plus cosine squared theta minus sine squared theta. So I'm cleaning up this. And then the bottom would be negative sine theta minus sine theta cosine theta, and then another minus sine theta cosine theta. So we could group those together. And what's happening in this situation is we're getting 0 over 0. At pi, at theta equals pi, what's happening is we're getting 0 over 0, which is indeterminate. So that it means we don't know if it's the top that's really 0 or the bottom that's really 0, because it's indeterminate. So what you have to do is you got to do L'Hopital's rule, because derivatives are limits, right? This is indeterminate. So if you were to try to figure this out without a picture, the picture I think made it very obvious. Then you would say, okay, well, then dy dx, we're going to take the derivative of the top. The derivative of the top is negative sine theta minus plus 2 cosine theta times negative sine theta minus 2 sine theta times cosine theta. Let's derivative the top. Derivative the bottom is going to be negative cosine theta. And you got 2 of these, so we could group these together and do a product rule. So we say minus 2 sine theta times negative sine theta, and then plus cosine theta times negative 2 cosine theta. Okay, so I'm just taking these derivatives. It's a little messy. We can go ahead and try and clean this up. Let's see. There's a negative sine theta and then minus 4 sine theta cosine theta on the top. On the bottom, there's a negative cosine theta, and then these guys actually end up canceling each other out, right? No, they don't. Sorry, minus plus 2 sine squared minus 2 cosine squared. It almost feels like it got flipped upside down. But let's go ahead and plug theta equals pi into this one again. And what we get is we get 0 minus 4 times 0 times 1 over, let's see, that'd be negative 1. And this would be positive 1 plus 2 times 0 minus 2 times negative 1 squared. And so you'd get 0 over negative 1, which is 0. So it is for sure horizontal based off of, and I'm not doing the slope of the curve. We've done that before, but I'm just proving without the picture that it is horizontal at pi, not vertical with L'Hopital's rule. So I don't really know if you're going to have to really do that much or anything, but that's the technical way. The picture gives it away, though. So now for the homework tonight, I'm going to give you guys a nice gift. We're not going to do this book assignment, okay? I'm assuming most people would rather do worksheets than book assignments. So I'm actually going to get rid of the book assignment, replace a worksheet, which also means we're actually just getting rid of a whole assignment. So it's not just the bonus of getting a worksheet instead of book work. It's just getting rid of that. So we're going to do worksheet 4.5. Okay. So this is lesson 4.4, but we're going to do worksheet 4.5. So there you go. Do a good job. You just lost a big assignment and also lost a whole extra assignment.